Hi, in this third lecture we'll actually create a confidence interval and I'll show you how one is made. We've talked about what they represent and then um, what they mean. Actually, I showed you how we didn't talk about how they were made, but once they're constructed, how to read them or what they represent. So now we'll actually go through how to construct one ourselves. So imagine for now that you are a quality engineer and you're going to work at a cereal company and you're trying to estimate the true mean fill weight of boxes of cereal. So, I mean, there is a true mean weight for all the boxes that you produce every day, but we're trying to figure out what that is. I mean, you have a label on your box, but does mu actually equal that? So, we're going to take a certain day and we're going to get a random sample of observations. So we're going to take a systematic random sample of 100 boxes. So what that means is if you're on an assembly line, maybe this is the fifth box that you took, and maybe you're going to take every fifth one then, like systematically get a sample that way. So let's assume by the end of the day you have 100 boxes. Okay, and then what I ended up doing is finding the mean of those 100 boxes to be 12.05 ounces. And I'm trying to build a confidence interval to contain the true mean mu of if we took every single cereal box and we found their average, what would it be? And again, this is just an estimate from my sample of 100 that day. So this is the sample mean fill weight, and I know I've been making, let's say, boxes of cereal for a long time, that the standard deviation for this population is 0.1. So in other words, I don't know what the mean is, but I know it comes from a distribution that has some mean mu and a standard deviation per box of 0.1. So this is what an individual box X looks like. It has this distribution associated with it. So now we just need a little terminology. Again, the sample mean is just a single number, and I'm trying to estimate the population mean. So what I'm going to do is build a 95% confidence interval for mu. So we need this information from the previous chapters that we've worked on, including the central limit theorem. Let mu represent the true mean mu for the amount of fill weight for all those boxes. I'm assuming that sigma equals 0.1, and I'm letting x1 through x100 be a systematic random sample of 100 boxes fill weights. So the value little x bar is the mean of the 100 fill weights. So again, imagine that we took x1 plus x2 plus x100 and divided by 100, and we got 12.05. So one of them could have been 12, one could have been 11.95, one could have been 12.21, one could have been 12.05. I mean, there's just a bunch of values from that distribution, just like we did with the normal. We sampled things from that distribution. I'm summing them all up, dividing by 100. I got 12.05. Now, if I did this for lots of samples of 100, I get lots of little x bars. I should distinguish them in different ways, but just let's just call it x bar 1, x bar 2, x bar 3, x bar 4. I mean, if all day long you just kept taking random samples of 100, getting their average, you would get an x bar, you would get an x bar, you would get, and all the x bars would be different from each other. But they would still have a distribution, and that's what we talked about in the central limit theorem. If I graphed all those little x bars, I get the graph of big X bar, and big X bar is just a graph of, again, take 100 sample, get a little X bar, get a little X bar. So for me, this big X bar represents the distribution of the graph of all the little X bars. And if I look at the graph of capital X bar, we said in the central limit theorem lecture that the mean of this graph of capital X bar should have the mean of the original graph, because all you're doing is pulling everything back into the center, and the standard deviation is actually going to squish up, right? It's going to get tighter because the regular distribution probably looks like looks like this. But imagine, again, you took 100 values, you averaged them, they're going to get quite close to the true mean mu. So this is the graph of x bar. It has the mean of the original distribution, it has the standard deviation, slightly less because I'm taking 100 observations, so it's getting tighter. This is probably the graph of x, and then this is the graph of x bar tighter. So this is the graph of capital X bar for many, many samples of size 100. So imagine I graphed a lot of little X bars. Okay, so let's just say the X bar I got today, let's say this is the 12.05. I mean, it could sit anywhere in this curve. I mean, it's somewhere in this curve, and just imagine it's sitting right here. So again, we don't know what the true mean mu is, but we know if I graph capital X bar, mu is at the center. So this graph is made up of lots of little X bars. If I take one little X bar and then put an interval around it, so go out so many standard deviations, go out 2 standard deviations, so that's about here, and that's about here, I would get myself a confidence interval. And in this case, you can see, I don't know what mu is, but it actually captured the true mean mu. And again, I don't know where little x bar sits. Every time you make an interval, you hope x bar is close to mu, so when you try to capture it, you're correct. But I mean, little x bar, I mean, it's very strange, but you could have taken maybe some problem with the machinery and you have an x bar weight out here. If you put a confidence interval around it, obviously you're not going to contain mu. So I think that's enough to start us out, and I'll go to the next one. We'll look at another little x bar, and then we'll actually build the confidence interval.